Hello, this is the ADVM 12, Unit 9 lecture on orientation tolerances by Todd Frazee. In this lesson, you will learn how orientation tolerances in GD&T control the angular relationship of features relative to one or more datum features, ensuring parallelism, perpendicularity, or angularity. You will see how orientation tolerances are applied using feature control frame and how they govern surfaces or features of size based on their specification. Unlike simple plus or minus angle tolerances, orientation tolerance provides precise and unambiguous control, making them essential for accurate part design and manufacturing. Objectives. By the end of this lesson, you will be able to identify, apply, and interpret orientation tolerances, complete orientation tolerance specifications, including one or two datum feature references, explain the effects of material condition modifiers when orientation tolerances are applied to features of size, and calculate the virtual condition for internal and external features of size which an orientation tolerance is applied. And finally, complete tolerance specifications that include orientation and form requirements on a single feature. A orientation tolerance, it's an angular relationship of one feature to one or more datum feature. Controls parallelism, perpendicularity, or angularity variation. The datum feature references are required, and independent tolerance zone for each feature. It's also applied to surfaces and features of size, and can achieve greater exactness and clarity of requirements than plus or minus angle tolerances can achieve. Orientation categories. So we have parallelism, perpendicular, and angularity. Basic angle of orientation relative to reference datums. We also have surface, center plane, or axis controlled by tolerance boundary based on feature type. Flat feature tolerance boundary is parallel planes, and cylindrical feature tolerance is a boundary that is cylindrical. The symbols and application. Angularity may be used for all orientation tolerances. Parallelism may only be used to indicate tolerance on features parallel to referenced primary datum. And perpendicularity only used on features that are 90 degrees angle relative to referenced primary datum. So it's important to know that it has to be in reference to a primary datum, so you can't use a secondary or tertiary datum in reference to these controls. Okay, feature control frames. The tolerance symbols on the left, followed by a tolerance value and a datum feature reference. It must include at least one datum feature reference. So in our example here, we've got a perpendicular, an angularity, and a parallel. They're all called to a datum A with a tolerance of 5/1000ths. So the tolerance zone, those position tolerances need to, orientation tolerances need to fall within. It's a parallel plane that's 5/1000ths separated between each other. Okay, orientation tolerances with position tolerances. So multiple segment feature control frames show two or more feature control frames stacked together. Single segment has one line of information. Multiple single segments shows tolerance symbol in each segment. And a composite has one tolerance symbol with multiple lines of information and is not applicable to orientation tolerances. So if you see it formatted, it'll be like the image you see there below the text. And we've got a position tolerance. It's a separate frame, and it's attached to a perpendicularity tolerance as well. But it can't be a composite frame where both those symbols would lie in the same box. Okay, orientation tolerances with form tolerances. The form tolerance to further refine feature requirements within allowable orientation tolerance. And it must be less than the orientation tolerance unless the orientation is applicable to a tangent plane. Okay. Okay, the orientation tolerance datum feature references. It must reference at least one datum feature, and the datum feature only constrains rotational degrees of freedom. Okay, application to surfaces and features of size. Orientation tolerance only controls indicated surface and maximum allowable variation shown in a feature control frame. The material condition modifiers are not applicable to the orientation tolerance. Always applicable material condition for a feature of size, though. And RFS, or regardless of feature size, establishes control of the center plane or axis. And MMC creates a virtual condition boundary. Material condition and material boundary modifiers. Orientation tolerance is assumed to apply RFS unless a modifier is shown. MMC or LMC symbol is placed after the tolerance value. The datum feature references are assumed to apply RMB unless a modifier is shown, as in the example on the left. MMB or LMB symbol is placed after the datum reference letter. Virtual condition in an MMC application. Establish when orientation tolerance is applied to a feature of size and includes an MMC modifier. Boundary of fixed size that cannot be violated by the tolerance feature surface. When it applies, it's at a specific or implied basic angle relative to the referenced datums and the size result of the combination effect of the orientation tolerance and maximum material condition. The virtual condition of an internal feature, MMC application, is orientation tolerance creates a virtual condition smaller than MMC size. Allowable orientation variation increases as the apparent opening size decreases. And related to AME of internal feature equal to greater than virtual condition. The virtual condition equals maximum material condition minus the orientation tolerance. Virtual condition of an external feature with an MMC application. The orientation tolerance creates a virtual condition larger than MMC size. The features appear to get larger as the orientation departs from perpendicular. And related to AME of external features equal or less than the virtual condition. So the virtual condition equals maximum material condition plus the orientation tolerance. A feature center plane and feature axis. The center plane is a theoretical plane at the center of an unrelated AME. Orientation tolerance applied at RFS on the feature of size applies to the center plane. The feature size, theoretically straight line, at the center of the unrelated AME. And the orientation tolerance applies regardless of feature size on cylindrical features, applies to axis of AME. And orientation and form tolerances, regardless of feature size, have effects that accumulate on features of size. Parallelism tolerance. Parallel features on an undimensioned model must be queried to determine the angle. Implied angle of 0 in orthographic views. Angular relationships between parallel features controlled with parallelism tolerances. Identify appropriate datum features. Apply the tolerance on features parallel to the datums using orientation or profile tolerances. Tolerance zones within applicable size and location tolerances. Parallelism applied to a flat surface. Parallelism tolerance specifies orientation requirements between flat and datum plane. A feature control frame attached to each surface to be controlled, and GD&T rule number 1 results in control of parallelism between surfaces. So in that case, the tolerance only usable as a feature of size departs from a perfect form boundary. And the tolerance zone is permitted to float within the size limit. Verification of parallelism of a flat surface. So here's an example of a setup where you're verifying parallelism. And I must note that first you have to check actually flatness, even if it's not called out. It's implied that a flatness tolerance is applied to both planes. So after you've done that, check the flatness on one side, you can come back and check parallelism. And you use a dial indicator on a height gauge stand on a surface plate. And it's kept at a fixed height and moved across the entire surface area. This only checks the orientation requirement and does not vary size tolerance. And there are other methods such as coordinate measurement machines that can be used to check this. Parallelism tolerance applied to features of size. Regardless of feature size, this establishes control of the center plane or axis of a feature. Maximum material condition or least material condition establishes a control of a surface relative to the virtual condition boundary. The feature control frame applied in a manner associating it with a feature of size and placed adjacent to the size dimension value or attached to the dimension line. And it could be attached to another feature control frame. Material condition modifiers and virtual condition. Cylindrical tolerance of specified diameter created when applied at regardless of feature size on a cylinder. Surface method and axis method are two methods of verifying when MMC or LMC is applied. And the surface takes precedence, but an axis is easier to report variations. Parallelism tolerance applied to a cylindrical feature of size. Parallelism controls cylindrical features of size orientation relative to the datum axis or plane. Position and orientation tolerances are separate, but both must be met. An orientation tolerance zone is only constrained in rotation not in translation. So it's only as the part rotates, not as it's from one place to another. Verification of parallelism on feature of size. Differing results are possible based on the surface of axis method. Sorry, rephrase that. Differing results are possible based on two methods. One's the surface method and the other is the axis method. The axis method is applicable to regardless of feature size applications. The surface method takes precedence for maximum material conditions and least material conditions scenarios. The verification process includes functional gauges for MMC and LMC. Take care in selecting the proper gauge design or measurement method. You need to determine the needed gauge diameter for the surface method and pins inserted into tolerance holes to verify gauge holes over pins. And remember, departure of unrelated AME from MMC results in an allowable increase in tolerance for a maximum material condition application. Okay, perpendicularity tolerance. You need to specify requirements of the feature at 90-degree angles relative to a datum plane or axis. The 90-degree angle is not assumed in undimensioned models. 90-degree angle is implied to basic dimension in orthographic views. So if you have a model, you're supposed to query it. You're supposed to actually measure it with a measurement tool within the model. On orthographic views, on a paper, it is implied that if it's a square corner and doesn't have an angle on it, that it is 90 degrees to the view. Okay, applied to surfaces and features of size, and use either perpendicularity or angularity symbols for 90-degree angles, but not both. Okay, perpendicularity tolerance applied to flat surfaces. Applied in the model with a leader terminating with a dot on the surface. Applied in orthographic view with a leader or feature control frame with extension line. And no material condition modifier applied. And must include at least one datum feature reference. Perpendicularity tolerance reference to one datum feature. Constrains only rotational degrees of freedom relative to the indicated datum. No assumed relationships for perpendicularity tolerance known. And verified a number of ways, including angle block set on a surface plate could be a method. And surface form must be contained within the tolerance zone. Perpendicularity tolerance is referenced on one datum feature. So the primary datum feature constrains two and secondary constrains 1 degree of freedom. This eliminates the need for directly applied angle tolerances. And verification is possible with an angle block, a surface plate that contains all degrees of freedom for the measurement with a dial indicator.